What's going on YouTube? This is IppSec, and I recorded this video a few weeks ago after a live stream on Twitch where we did some instant response on the Hack the Box Pro Labs offshore. Essentially, on one of the Linux boxes we came across some malware that was running, but the odd thing about it is it had a deleted file it was based off of, so we couldn't identify exactly what that malware was unless we extracted it from memory, which we used DD to do. I later found out you could have also just copied the proc self exe file to extract it. Additionally, we extract the heap memory so we can get some information about the malware itself to find out it is Metttle/Meterpreter. We'll also confirm that by doing some Ghidra and GDB against it just to kind of explore how it works. So hope you guys enjoy this video. So here we are on Nix01. If I do a ps-ef on forest, we can see a few suspicious things right at the bottom. The first is, let me do a less-s. This Splunk reverse shell Python script. We looked into that on stream. It's definitely suspicious, but the main thing that I found really interesting is this temp.jd.dod file, because I tried to go view it. So if I do ls on it, it doesn't exist. If we do lsla on temp, we see that file just does not exist. So I kind of wanted to know exactly what this was. So my first thought was I went into proc and then 14180, because this is going to be the directory associated for this process. And then we went into like the file descriptors and tried catting a bunch of them, see if we saw any info here. Spoiler, we didn't. We could do lsla and see what they are, but nothing really helped here. After a lot of digging, we wanted to like recover this exe. And my first attempts were, well, maybe I can like view this memory file, and I can't. I try to cat it, it doesn't work. I do like dd, and we do if equals mem. Let's set the block size equal to 1 and try to copy 10 bytes out of this. And output file temp output. We see we can't read it. But what I did learn is if you go to the location where this process writes to, you can dump things out of it. We did a lot of other things, like I couldn't do GDB to just dump it that way because we don't have GDB installed in this system. And of course, we also don't have any instant response tools installed in the system. So those would probably be the ways I would do it. Or maybe I do it this way now, just because I found out. So if I do a cat on this maps file, this is going to tell me where everything is, right? We have it telling me this exe is deleted and it's at this location. So the one piece of information you'll probably need for the next piece to make sense is this dollar double parentheses will just translate hex into decimal. So what I did was a dd, and we can say input file is equal to mem, block size is equal to 1, and then we want to skip all the memory until we get to this spot. So we're opening up the mem file and then not reading from it. We're just skipping all the bytes up to here. And then this is 9,000. This is 8,000. So I'm just going to count for 1,000. So we're just going to read. We skip here, then read the next 1,000 bytes. And let's see, bs skip. I think all we have to do is specify output file now. So temp output. And now we have a copy. So I could do a file on temp output. And we see it's an elf, which is good. That's like a Windows executable. So everything's looking good. The other thing I did was like an XXD on it. And we can see it's really small. Like most of that 4,096 bytes is just nothing. And it's that way because I guess that's the default page size for memory. So I can't allocate less than that in memory. But right now I'm thinking this is some type of stage thing, because normally an executable, when you XXD it, does not fit on your screen. So I know this is some type of stage thing, meaning it's just going to either make a request out or set up a listener and then download shellcode or receive shellcode and then execute it, right? Because there's not much else you can do with this amount of space. So we still don't know exactly what it is. The next thing we could do is dump the heap. So the heap's going to be where like all the memory stuff is, and there's probably going to be an L file embedded in this heap as well. I don't actually know that. I haven't dug that far into it. We just verified it was Metttle and called it a day. So, and Metttle is Meterpreter for Linux. So we're going to copy this heap, and this is 4,000. Oh, this is big. I wonder if I can do like subtraction here. I did not do this on stream. We just copied 3,000 bytes, so we didn't copy the whole memory allocation. Now we are. And we have to prefix this with 0x. We can call this heap. That looks like it may have worked. Strings temp heap less. Get a bunch of headers. There's the passwd. This is how we knew it was Metttle. And then we have where it's talking to, setting up some file descriptors. I guess it's on port 4433. Or maybe it's 443 in a weird like strings thing, displaying different things. But we can see we have its memory. So just from those two commands, we're able to grab a bunch of good information. Do I have bin walk on this system? I doubt I do. So what I'm going to do is pause the video, and we're going to copy output and heap to our box. Apologies for the sloppy cut. When I did the stream, this was the first time doing this, and then I kind of learned a little things. I did it a bit smoother in this recorded video that you're watching now. And then after I finished, I kind of tweeted about recovering files, and someone's like, why don't just use the exe in the proc? And I was like, wait, what? So if you wanted to do that, it's a much easier way. We can go in, oh, it looks like there's a second person doing it, or it's the same person. But we can go into proc 14180, and then we are using the mem file and the maps file, but there's also this exe, which is just a symlink to the executable section. So if I cp exe to dev shm, and I'm going to call it jd.dod, and we go into that directory, we have the file here. So yeah, this is the other way to do it. We could xxd it and see it kind of looks the same, I guess. I think I did like temp output, xxd temp output. We probably have to head dash 20. Let's do 15, 13. That looks fine. So xxd this, do the other one, and we can see they look identical. T4, T4, 4. The ASCII is matching up. I'm assuming these other bytes match up as well. So just a different way we could extract it. So now let's switch over to my other machine where we will reverse this binary and find out exactly what it is. So now we have both the files on our desktop. The output is the elf, heap is the heap, and remember, heap had the IP address, but the main thing we want is output. So I'm going to open it up in Ghidra because that's normally my go-to for any type of reverse engineering, and on stream we did not really like this Ghidra output, and we switched to a different application. But again, I just want to show you kind of a summary of what we did. And this looks like the binary. So I guess it was remembering where we were at. But this is what it looks like. Let's see. I'm trying to make sense of it. I can't really. I know this is a syscall number, but not sure why I know that from Ghidra. I just know that from reversing it outside of Ghidra. If we look at the shellcode, it makes a bit more sense. I think all the Metasploit shellcode was handcrafted, so looking at the disassembler view would be more helpful. This is pushing A2, this ends up in EAX, and then every time you see int 80, that's it doing a syscall. So if we look at A2, if we do echo, let's do 0xA2, it is 162, and I go Google Linux syscalls. This is the other mistake we had made in the stream. We went here and went to 162 and saw, oh, this must be a sync, right? But if we do a file against this, we know it's 32-bit. And on this, it says 32-bit syscalls coming soon. So if I do Linux syscalls 32-bit, we can take a look at, let's see, maybe this. And we want to go to 162. We can see that's nano sleep. So that's a sleep. If we go back to Ghidra, do we have any others? Let's see. Let's go int. So 66 and 2, I'm guessing. So going back here, 2 is fork. And we need to know what was it? 66. 102. If we look at 102, that is socket call. So this is the one we actually want. But the whole decompiler view sucked. So the tool we had ended up using, let's just exit this, is called Cutter, because it supports 2 different formats of decompiler. So you can get it at cutter.re. We saved it. Let's see. Downloads Cutter. We can analyze it. Let's see. It's in home IPsec. Home IPsec stream. Oh, come on. Cancel. Select. Stream IR output. So let's open this file. We can analyze it. And this is, if we go down the bottom right, we can change between Ghidra view, which is this, and we can do JS deck, which is the R2 decompiler. And we can see this is much better. Like, it's converted the int 80 calls to be actual syscalls. And then we can see like 0x66 that's sending that there. This goes into EAX. 66. So it's much more apparent what this is doing. And then it does a weird thing, just like the last one, because it's handcrafted assembly. If we wanted to, we could go over to Google, and I did not know where this was when I was streaming, but after the stream, I decided to look at it. So if I go Metasploit, GitHub, source, shellcode, I think this is going to pull it up. So this is the Windows shellcode. I'm going to go back here. We'll switch to Linux. And we want 32-bit, so that's IA32. And we can do probably single reverse TCP shell, I would think this is, or maybe this is TCP. Let's see. How many reverse are there? Sock reverse and TCP shell. We can just look at this one. You can see kind of how it works. It's got actual documents. So when you do the socket call, it takes things in reverse order. So at this memory address, it's pushing it to the stack. And that is 127.0.0.1. 7F, I should make this bigger. 7F is 127. Then you got 0. Then you got 0. Then you got 1. And then it pushes the port, just converts this into hex and pushes it there. So knowing all of this, let's go and reverse this binary. So I'm going to chmod + x output. Actually, before we do that, we thought this was Metttle just because of the heap. If we grep it, it's got the string Metttle in it, which screams Meterpreter. We can create our own copy, so MSFVenom, then -p or -l payloads to list payloads. And I'm going to grep it for Metttle. And I'll do a -i because I'm not sure if it's a capital M or lowercase m. But we can go and generate our own shellcode for this. So let's see. We want to do Meterpreter. Let's see. Linux x86. This is going to be the stage list payload. We don't want those. We want the staged payloads. So we definitely want to see a lot of slashes like this. So let's see. The difference is a slash after Meterpreter. And we can show the difference once we generate this. So I do MSFVenom -p, specify my L host, so 10.10.14.8. L port, we'll do 9001. Format is ELF, output, generated stager. I should call that staged, but it's fine. So if I do file against this, we have that ELF. And remember, output is from the actual target and generate stager is ours. So if I just XXD it, we can see what it looks like. It stops at C0 and it ends with like this, right? So if I XXD output, we get a lot of zeros, right? But eventually, at the top, it stops around C0. Same exact byte it stops, and it stops with 80, right? So this is looking very similar between these two. So we know this is a staged payload. So what we could do is a GDB, and I'm going to do it against, we can do it output. Let's see, GDB /output, and let's see, I'm not sure you'll be able to see this because of how I have the recording set up. You cannot, but what I'm doing right now is disconnecting the NIC from my computer. So if I do IP-ADDR, we should see this is now disconnected. If I ping 888, I can't. Whenever I reverse malware, I like just disconnecting the NIC, and I also took a snapshot because I'm running an executable from a user. So we're going to do GDB on this. Oh yeah, this was a stripped binary, so opt Ghidra. I'm just going to get the memory address from Ghidra. We could probably get it from Cutter. I just know where it is in Ghidra. Let's open this. And we'll want to go to output. So home, IPsec, stream, IR, output, analyze. Yes, come on. So many prompts. Exports, entry, and then, let's see. Where does this start at? 54. So 8054. So if I run this, let's do, where's GDB? Run, Control C. So it's got the same exact memory location. So I'm going to break *0x804, 8054, I think. 8054. Awesome. So I'm going to run. And now we broke at the entry point right here. So we see push 0 pop ESI, push, 0xa, yep, then pop ESI, then a XOR. So we are where we think we are. And I'm going to int 80. And when I go here, I can go up to look at EAX. EAX is set to 66. 66, let's see exactly what that is. Echo 0x66, 102. Let's go back to our shellcodes, syscall list. 102 is the socket call. Awesome. So we are where we think we are, but I don't see any like IP addresses in the stack. So I'm just going to go past this syscall because maybe this one is just like opening the socket or doing something. I'm guessing it matters based upon this number. But I'm going to keep stepping through the code. We get to the next int 80, which is doing a syscall. And this number is different. And also, we see right here, OA, OA, OE. OA is 10, OE is 14. So that's 10, 10, 14, and then AA would be the user's IP address. So if I do AA, it is 170. We can do OAC 10, OE, confirm 14. So now we have confirmed or ran this 100% confirmation. This is going to be Metttle just because all the shellcode lines up. And just from this staged payload, we get the IP address it is calling out to. I think the next one was port. I don't know exactly where that is. The port was like 4433. And I'm guessing that's this, but doesn't look right. Yeah, it's probably like a signed number or something. But that's pretty much as far as we went. So hope you guys enjoyed that, enjoyed how to take that file that's running on a Linux system, but someone deleted the executable. So you can take it from the memory and then just doing that type of analysis. So take care, guys, and I'll see you all next time.